All right, let's take a look at the next few examples. Example 10, determine whether the following integral converges. All right, so this one can be, well, again, doesn't say specifically to use the comparison test, so we don't have to do that. Comparison test is useful for when the function you're integrating either appears to be a very nasty integral, or perhaps you can easily compare it to a function that you do know its behavior. So I always like to try comparison test first, see if it's possible for me to construct an inequality that compares our given function, e to the negative x squared, with another sufficiently well-behaved function. Okay, so let's see if we can do anything here. So what I would do is I would first grab x squared, or negative x squared, let's say. So negative x squared. And what can I compare that to? Well, something simpler. What about negative x? Is negative x squared less than negative x? I'm going to put a little question mark here. I'm going to put it off to the side. Well, we can try this. And let's forget about the negatives. Let's just grab x squared and x. We'll deal with the negatives secondly. So is x squared always greater than x? Well, it's not always greater than that itself. For instance, numbers such as a half, when you square them, they get smaller. But numbers such as 2, when you square them, get bigger. Even if I pick a number that's very close to the number 1, such as 5/4, if we square it, we get 25 16ths. And you can compare this by getting a common denominator here. A common denominator here would be 16, so I have to multiply by 4 before, so 20. So you do see that this result here is in fact bigger. So the dividing line, so to speak, where squaring things flips from getting bigger to getting smaller, is when the number that you're squaring is equal to 1. Numbers that are greater than 1, they get bigger when you square them. Numbers less than 1 get smaller when you square them. But really what I should say here is an absolute value. All right. So what I'm going to say is that this quantity that I had written down is not always true. Really, for values of x that are greater than 1, this inequality is true. So if x is greater than 1. Okay? So now this inequality, so what this essentially tells us is I can't use this inequality for the entire integral because we're going from 0 to infinity. So this caveat right here forces us to split our integral into two integrals. So let's go ahead and immediately do that. 0 to 1, e to the negative x squared dx, plus the integral from 1 to infinity, e to the negative x squared dx. Now this integral right here, this converges. And it's not improper. An improper integral is an integral where our domain of integration is an unbounded interval, or our function that we're integrating approaches, its value becomes unbounded within our domain of integration. Neither of these two things happen. This converges since e to the negative x squared is continuous. That means it doesn't have some infinite discontinuity. Since this is continuous on a bounded interval. So there's no way that this could somehow create an infinite area. So this converges. So really the problem shifts to focusing just on this integral. All right. So let's continue with our inequality here for a moment. For x greater than 1, we know that this must be true. And then we can multiply this inequality here, just this inequality, by -1. If we multiply by -1, we get negative x squared and negative x. But remember, with an inequality, you have to flip the direction of the sign. So we get that. Now that we have that, what we'll need to do is, well, try to build the function that we have. We don't have a negative x squared that we're integrating. We're integrating e to that. So we can do another step here, which is where we can actually exponentiate everything. And exponentiating, since that in and of itself is an increasing function, we don't have to flip the sign of the inequality. So we'll exponentiate, or basify, whatever you want to call it. I have no idea what that's called. We have that. So we've just shown, and actually, I have a strict thing here. I'm going to go ahead and put inclusive. I'm going to put inclusive because the inclusive part doesn't actually contradict anything, right? Is 2 greater than or equal to 1? Sure. I mean, it's better to put this, I guess, but is this wrong? No. It's just a little bit more flexible. So I'm going to go ahead and just change those really quickly. Because again, when I see the strict, it means that it's always strict. For here, there actually could be the same value. For instance, when x is 0, we have e to the 0 and e to the 0, which is 1 and 1. And if I did this, this is wrong. That's wrong. So actually, we do want that. So just be careful of that. Most people aren't nitpicky about that in a Calc 2 setting, but I do think it's important to think about. Okay, so we've got this inequality now. And the other thing that we do want to just emphasize here is that whenever you have e raised to something, this is always bigger than 0. Okay, and that's what we need for the comparison test, is we need an inequality between two functions, and then we have to ensure that both of these functions are positive. Okay, so let's go ahead and compute this, the integral of this term, because the integral of this one, while it is possible to do, we don't have enough information to do this in Calc 2, and even if you get to Calc 3, you can figure this out, but it is a little tricky to do. So we can't integrate this, so let's choose to compare it to this function and integrate this one. So we're going to just kind of put that a little bit on hold, and let's go ahead and compute 1 to infinity e to the negative x dx. Well, using a limit as r goes to infinity, I'll also do the antiderivative, negative e to the negative x from 1 to r. Evaluating, we should have negative e to the negative r minus, so plus e to the negative 1. So this is the limit as r goes to infinity of 1 over e minus 1 over e to the r. Well, as r goes to infinity, e to the r gets very large, but 1 over e to the r gets very small. So this term here actually goes to 0 in the limit sense. So this turns into just 1 over e, which is a finite number, so it converges. So this second integral converges. So, making a full sentence here, a little conclusion statement, I'll say, since 0 is less than or equal to e to the negative x squared, which is less than or equal to e to the negative x, and that what do we have here? And that this integral from 1 to the infinity e to the negative x dx converges, by comparison, so must the integral 1 to the infinity of e to the negative x squared dx. Therefore, since both the integral from 0 to 1 e to the negative x squared dx and the integral from 1 to infinity of e to the negative x squared dx converge, then the integral from 0 to infinity e to the negative x squared dx converges. Sort of putting it all together.